So here's the connection between work and energy. It's this section that makes that very important connection. Let's get right to it and define the kinetic energy of an object. This definition is for non-relativistic speeds. Namely, speeds that are very small compared with the speed of light. This means much less than, the way the physicists write much less than. This is the speed you're interested in, the speed of the Leisure or whatever, and c is the speed of light. Speed of light is 3 times 10 to the 8 meters per second. Most speeds that we're used to dealing with, a car going down the highway is going maybe 30 meters per second. So is 30 small compared to 3 times 10 to the 8, 300 million meters per second? Well, yeah, it is. So this non-relativistic approximation for the kinetic energy is a very, very good approximation of the kinetic energy. In a later chapter, in the second semester, right near the end of the semester, we will talk about relativity and talk about the relativistic kinetic energy. But for now, this is what we need in our everyday world. The kinetic energy is defined as 1/2. The kinetic energy of an object is defined as the mass of the object times the speed of the object squared. So there's the speed measured in meters per second, and we have to square that to form the kinetic energy. And there's a 1/2 out in front. There are all kinds of good reasons why this definition of the kinetic energy is the right one. The WorkEnergy Theorem is one good reason. When we do relativity is another good reason. It has to have the half there in order to be related in a simple way to the work. Just 1/2 mv squared. This kinetic energy is always positive. So if you have an object that's moving this way with the speed v and it has a mass m, its kinetic energy is 1/2 mv squared. If you have an object that's moving in the negative x direction, guess what? Its kinetic energy is 1/2 mv squared. The energy does not care which direction you're going in. Which of the following statements is true concerning kinetic energy? The kinetic energy of an object is directly proportional to its speed. Well, that's false, because the kinetic energy is proportional to the square of the speed. The kinetic energy of an object is expressed in watts. Well, we haven't even introduced the unit of watt yet. That's not true either, because it's actually measured in joules. Let's prove that. Well, we can prove it right here. I think I actually mentioned it. Yeah, I mentioned that this kinetic energy is measured in joules, but I didn't prove it. Let's prove it. What are the units of kinetic energy? Well, 1/2 doesn't have any units. It's just a pure number. Mass is measured in kilograms. Velocity, or speed, is measured in meters per second. But we have to square those units, because velocity is squared. Well, that is kilogram meters squared per second squared. But that's nothing other than our old friend the joule. And we did an exercise to show that the joule was exactly the same as this. So the kinetic energy is actually measured in joules, so that one's not true. Kinetic energy of an object always has a positive value. That is true. It's always positive. No matter what direction it's going in, you always consider the kinetic energy to be positive. The kinetic energy of an object always equals the object's potential energy. Well, we haven't even introduced the potential energy, but it's not true. We will introduce the potential energy in just a second. 6-3, state the work-energy theorem. Here's the connection between work and energy. The work done, and there's a very nice derivation of this result in the textbook. I'm not going to go through it. We will, however, justify this result in a particular example. The work done by the net force. So this is a very important work. It's not the work done by friction. It's not the work done by gravity. It's not the work done by the normal force. It's not the work done by tension. It's the work done by the net force. And what's the net force? The net force is the vector sum of all the forces. So this is the work done by the net force on an object equals the change in its kinetic energy. So here's the work done by the net force. We write the net force using this sigma, capital sigma, times the sigma f. That means the net force, and that's the work done by the net force, equals the change in the kinetic energy. What do we mean by that? Well, we always use this symbol delta to mean final minus initial. No difference here. So this is our final kinetic energy. We're going to write that KEF, where F stands for final, minus KEO. Instead of using an I for initial, we're going to use O like we did in Chapter 3 for kinematics problems. X and X naught. X is the final position, X naught is the initial position. So this is the initial, this is the final, and we take the final minus the initial to get the change in the kinetic energy. And what the work-energy theorem states is that that work done by the net force is that change in kinetic energy, meaning that it's the final kinetic energy, 1/2 mv f squared minus 1/2 mv naught squared by the definition of kinetic energy. So, for example, if we have a net force in this direction on that plane, and we got a normal force, we got gravity, we got some kind of pushing force on it. If this is the net force on that plane, then the work it does is going to be equal to the difference between the final kinetic energy and the initial kinetic energy. All right, let's go back to our crate problem. 120 kilogram crate rests on the bed of a truck accelerating at 1.5 meters per second squared over a distance of 65 meters. Find its final speed. So we're going to do this the old way, which I hope to convince you is the hard way compared with the new way that we have of looking at it. We can use the equations of kinematics. The final position is 65 meters. That's the final value of x. So x is in this direction. The initial position is 0 meters. The initial velocity, it's starting from rest. So that's 0 times t, and equal plus 1/2 the acceleration times t squared. Well, this term is 0, this term is 0. I can solve this equation for t by multiplying both sides by 2, by dividing both sides of the equation by 1.5 meters per second squared, and then by taking the square root to find t. So here it is. T is 2 because we'd already multiplied by 2. We divided by 1.5 and we took the square root. So the algebra gives us 9.3 seconds for the time that it takes to speed up over this distance. What's its final velocity? We're asking for its final speed. Well, we can do that with the other equation of kinematics. The final speed is the initial speed plus the acceleration times the time. We now have the time. Plug those numbers in, and we get that the final speed is 14 meters per second. Well, let's verify the work-energy theorem in this particular instance. We calculated the work done by friction, the normal force, and gravity. You'll remember, go back about 5 slides, and you find it. We found that the work done by friction was 11,700 joules. We found that the work done by the normal force was 0, because the force and the displacement were perpendicular to each other. Same thing with gravity, that was 0. So that's the work done by the net force. We've added up the work done for all 3 of these forces, and 2 of the 3 had 0 work, so that made our lives a lot easier. The change in the kinetic energy. So remember that the work-energy theorem states that the work done by that net force is equal to the change in the kinetic energy. Well, now, having done the calculation to find the final speed, we now can find the change in the kinetic energy. It'll be the final kinetic energy, 1/2 mass times that final speed. We found that to be 14 meters per second squared. Minus 1/2 times the mass times 0 meters per second, quantity squared. The reason that was 0 because it started with no initial velocity and no kinetic energy. The velocity is 0, the kinetic energy is also 0. So lo and behold, these 2 numbers are the same. Not sure what to say. They need to be they must be the same if the work-energy theorem is valid. And I posited the work-energy theorem for you, asserted for you that there's a derivation in the book, told you that I would give you an example that verified the work-energy theorem, and this is it. So this is just one example of, but it's valid in all instances anyway. Okay, let's do another example. A 474 kilogram space probe with initial speed 275 meters per second experiences a 0.056 Newton force over displacement of a whole lot of meters. Find its final speed. This is very similar to the previous example. There's force, just a single force acting on it. That's the force. That's the distance. Cosine of the angle between the force and the distance are parallel to each other. The angle between is 0. Cosine of 0 is 1. That gives the work done. And using the work-energy theorem, we can find the final speed. How do we do that? Well, the work done by the net force is equal to the change in the kinetic energy by the work-energy theorem. So that's the final minus the initial. We're actually starting up at an initial speed of 275, and we're trying to find its final speed. So this is 1/2 times the mass times the final speed squared, which we don't know what it is, minus 1/2 times the mass times the initial speed, which we do know, 275. So now we have what might look to be a rather ugly equation to solve. We have the work done by the net force. That's this thing I've just circled. We've written an equation for the change in the kinetic energy, which is this mess here. Those have to be equal to each other by the work-energy theorem. So I got this huge ugly mess here equals that mess on the right-hand side, but we only have one variable. It's the final speed, right there. So to solve for that final speed, I'm going to add this whole term to both sides of the equation. So I'll have to add that term to this term on the right side of the equation. Then I can multiply both sides of the equation by 2 to cancel the 1/2. Divide by 474. and both sides of the equation, then we'll have VF squared. And then to find the answer, the final answer, we take the square root of VF squared. And that gives 805 meters per second. So that's how to go about solving a problem using the work-energy theorem. You work out the algebra yourself. I gave you some hints on how to work out the algebra. Conceptual example. A satellite is moving about the Earth in a circular orbit and an elliptical orbit. For these two orbits, determine whether the kinetic energy of the satellite changes during the motion. All right. Here it is moving in a nice circular orbit. In this case, the force holding the satellite in orbit, what force is that, I might ask? You might say, isn't it gravity? And I say, yes, it is. Gravity is pulling the satellite toward the center of the Earth. The displacement of the satellite is always perpendicular to that gravitational force. So what's the work done by the gravitational force? It's 0. So the work done is always going to be 0 in this particular case. And the satellite, by the work-energy theorem, there's only one force acting on the satellite, it's gravity. So the work done by the net force is nothing other than the work done by gravity. That work is equal to 0, which means that the change in the kinetic energy is going to be 0. What does that say about the kinetic energy? It says that the final kinetic energy minus the initial kinetic energy is equal to 0. But you can just add the initial kinetic energy to both sides of the equation and determine, therefore, that the initial or the final kinetic energy is the initial kinetic energy. Kinetic energy doesn't change. It's moving at a constant speed. It's in uniform circular motion, like we did in Chapter 5. All right, well, what about over here? Planets actually, and satellites actually orbit in ellipses, not circles, with the center of motion at one of the foci of the ellipse. So here would be the two foci, one here, one there, and the Earth, in this instance, is providing the gravitational force for the satellite. It's at one of those two foci. So as the satellite goes around in this elliptical orbit, at this particular point, as it's approaching the Earth, coming closer to the Earth, S, the displacement, and F, the gravitational force, are not perpendicular. In fact, the force is in the direction of the acceleration, not perfectly aligned, but it's in the basic direction of acceleration. The angle between them is between 0 and 90 degrees. And as we talked about before, with an angle between 0 and 90, you're going to get a positive amount of work. Whereas over here, as the satellite is regressing away from the Earth, the displacement, the direction of the velocity, each individual displacement, and the force are at an angle that's greater than 90 degrees. And we'll get a negative amount of work here. So, what does a positive amount of work do to the kinetic energy? That force is in the direction of motion and causing it to accelerate. So the satellite's going to be accelerating. So it's going faster and faster. And then out here, it's going to decelerate or slow down. Let me just, because accelerate can either be positive or negative, let me just say is that the satellite speeds up. And over here, the satellite slows down. Okay. So we can now answer the question, for these two orbits, determine whether the kinetic energy of the satellite changes during the motion. Well, the kinetic energy only depends on that speed. It's 1/2 mv squared. And so when it speeds up, that speed is changing, and the kinetic energy is going to increase, in this case here, as it's approaching. So it certainly does change. The kinetic energy increases as it's approaching, and the kinetic energy decreases as it is regressing away from the Earth.